Okay, so lots of things which we heard already today are also part of my presentation, because it seems like there are some fundamental concepts and they were all identified, like flow duration and erosion rate, critical shear, and how we marry these two concepts. So don't be surprised if you see something similar. The only difference is that we're using CFD for our analysis, which gives you actually a higher resolution to solve the problem. So the first subject I want to talk about is how can we use this concept to define Bankfull width? There are lots of philosophies out there what to do. We heard maybe to use the Q2 or Q1, and then or just go out into the stream and measure, and then add 1.2 times the Bankfull width, and maybe add some 2 feet or something. But what we try to do is to get a better understanding what that is, and maybe use a more scientific basis for that idea. Again, lots of things we heard about already. So let's start with that concept. So this is a general channel geometry where we don't know at this point what the Bankfull width is going to be, and we also don't know what the Bankfull depth is going to be. So let's run some flow through that channel and measure, in a three-dimensional model, let's measure what the shear stress distribution is on the channel bed. Let's run more flow through the channel, and at a certain point, what is going to happen, that the shear on the channel bed will equal the critical shear of some bed material. It could be gravel or cohesive material. And then if you run even more flow, what would happen, that critical shear is exceeded, and we have to assume that something happens with the channel. It starts kind of deforming or changing. And even with more flow, that would be more exaggerated. But what was your name? I'm sorry. As Holly mentioned, another critical component for this is the duration, because you have to know how long does the flow last, or in terms of stream power, how much power is necessary to create some deformation. And eventually, there's a sweet spot somewhere, like a maximum, where the width would be established, where the channel forms. And with that, you could determine the width and the depth. So, but what's needed is flow duration. Should come up in a second here. It's a big file, so hopefully it comes soon. Oh, here it is. Okay. So flow duration. It's actually, the basis is we have some a hydrograph, and then you can do a flow duration curve, but the flow duration curve can be also converted into a PDF. So which shows here, that's like a PDF or a probable mass function. And what that shows is kind of on the x-axis you have the flow rates, discharges, and on the y-axis you have the duration. So for instance, somewhere you can imagine that the high flows, like maybe the Q50, the Q100, they don't occur very long, but there are some lower flows or mean flows, they occur way longer over a certain duration. So let's say a Q1, and then what we do is we pick, of course, these bins, so these durations, they can be, these increments can be randomly picked. I mean, these increments can be picked in maybe in shorter periods, but in order to speed up the work in CFD, because CFD is actually very time-consuming, so we were a little bit more generous picking these increments. And then what we did, we ran flows through the channel in CFD for different discharges, based on that flow duration, and measured the associated shear stresses. Now, the big advantage of this is that, again, you get a shear stress for every element. And why this is important, because not every shear associated with that flow generates erosion. Only the shear which exceeds the critical shear generates erosion, of course. So another factor in this whole process is we need to define an erosion rate. And what we picked here is a pickup function or erosion rate function. There are several functions in literature. We used here the Van, but this can be done through a field test. I mean, you can go out there like with the jet erosion. You can use even an ISDD, or you can take a sample, bring it back to a lab, and you get an erosion rate based on your field test. And then the next step is to marry these two, as I mentioned. We marry the flow duration with the erosion rate. And for example, here again, if we pick that low flow in that channel, and the flow throw is, so the shear generated by the low flow is lower than the critical shear, you see that little red dot, nothing would happen because it's just not powerful enough. So if you pick another flow, in this case, you're right at the point of critical shear, and then with a higher flow where the critical shear is exceeded, you will see some deformation of the channel. Let's pick the next one. Again, this is also always associated with flow durations, because that's already incorporated, because you multiply the erosion rate with the duration, and then here more erosion volume is eroded. And for 5, for this discharge, which already exceeds that mean, you might see a little bit less erosion volume because the duration is getting shorter. And if you pick like a very high flow, you will not see lots of erosion volume, because you just, although you have a very high power in your stream, but it doesn't last long enough to get to generate that volume. But the bottom line, somewhere, if you plot all these erosion volumes, you will have somewhere a maximum of all these volumes. And that's, I think it was also identified in the previous presentation, that's what we call the effective discharge. And then we take this effective discharge and run that through our channel, and that would then give the flow depth and the Bankfull width. So with this discharge, we could define that, with this method, we can actually define what that Bankfull discharge is. So it's maybe a Q, but maybe not a Q2, something else, because that's kind of just based on that maximum erosion volume. The next step is to see, to associate a time exceedance probability to that top width. So this shows here the discharge and top width line chart. And if we now take the flow duration and that top width versus discharge curve and merge them, we can actually determine the percentage of time exceedance of that top width. So we were very fortunate to work with Washington DOT, and Julie sent us some valuable data, and we wanted to test how this concept works. So this is the site. This is probably Julie knows more about it. So it's the Fisher Creek in Washington. Then we also got a HEC-RAS model. We also got, this is the section we kind of wanted to test here. We got a nice cross-section of HEC-RAS. So this was the channel bed width, 6.1. We also had good information about the bed material, gravel. So it was the D50 was a 3.1 inch with a critical shear of 25 Pascal. We also had some roughness values. And then, more importantly, we also had the hydrograph, so we could actually develop a flow duration curve. And these are the shear stresses we computed in CFD for multiple discharges, as I mentioned earlier. And we got, actually, this is the chart of the erosion volumes, and as I pointed out, the maximum, we picked the maximum point for the channel forming flow, and we computed a 1.7 feet Bankfull depth, which is pretty, matches pretty well what we got from the Washington data. So this concept, or very similar concept, can be also applied. Oh, and one more thing I forgot about is we want to also see what the time exceedance probability was for that Bankfull width. And if we put that, if we take the 1.2 times plus 2 feet, which resulted in 15.2 feet, and that top width would be just exceeded 0.56% of the time, which is, we had a flow duration over 2 years, and that's just 4 days. That top width would be exceeded. So another stream instability is head cut. And we just want to show you a concept how this idea can also work to look at head cut migration. This slide shows a little bit the head cut mechanism, but I think most of you are familiar how that works. So you have a lesser erodible strata and below a more erodible layer. And as the flow plunges, like a weir flow over that lesser erodible strata, the more erodible part gets undermined and creates a head cut, and the channel and that cut moves upstream. So for this model, we have some assumptions. We assume at this point, I mean, this model, of course, can be more sophisticated in the future, but what we assume now that the shape of that cut doesn't change and just gradually moves upstream. Again, we use, and then we would then compute that bank erosion volume, and then with that we can actually back calculate how far the channel moved upstream. We use again CFD, and it just takes a while till this loads. Just bear with me. These are huge files, so. Oh, no, so and then of course, as pointed out earlier, we also need the flow duration, which is again going to be married with the erosion curves. And let's see, a second here. This should show. Here we go. This shows a CFD modeling of that head cut, and then we can compute shear stresses on the riverbed, and then again we take shear stresses. Here we have the erosion rate curve and all the flows which generate a shear which exceeds the critical generate that volume, so the erosion volume. So we take again, we multiply the duration with the erosion rates for several discharges, and then ultimately we will get the erosion volume distribution. In this case, we would take the entire volume, and because that's the material which eroded during that time period, and with this simple equation, so we know the height because we assume that the geometry didn't change, we can actually back calculate the head cut movement. In the next step, what we can do is kind of calibrate our erosion function. Because if we have some field data available, we can actually measure how far that head cut really moved. And if we know the associated flows, so the channel essentially did the erosion test for us. So we can go back and do some corrections to our erosion rate curve, and calibrate that erosion rate curve. So that's all I have. And if you have any questions, just please feel to ask. Okay. Yeah, sure.
For now, what was your assumption about sediment coming from upstream when you're?
At this point, we didn't assume that sediment comes from upstream.
Clear water.
Yeah, it's clear water. Yep.
For headcount, where do you actually measure the shear stress? Because maybe computation shear stress are everywhere.
Yeah. Well, at this case, we just pick the maximum shear stresses in that zone. So, but the model can be refined. It can also, we can add maybe a sandslide model to it. So it's just wanted to point out the concept here, what we can use. Yep.
Just a comment on more than one paper we're talking about here. I've had a little bit of experience with stream restoration projects, not designing them, but seeing how they work. Urbanization of the watersheds is really a big concern when you're planning these, because new roads and bridges are often in areas that are developing. So just keep that in mind as you're trying to apply these, because I've seen stream restoration projects washed away. Very thoughtfully designed using Roskin or other techniques that are well accepted and well thought out.
Thank you. Okay, thank you.